A very good morning to one and all. I welcome you all for the last session of classical mechanics, session number 35. In this session, we will solve some more numerical problems of constraint motion using Lagrangian equations of motions. The main objective is to solve Lagrangian equation of motion for constrained motion. By the end of this session, you will be in a position to solve Lagrangian equation of motion for a constraint problem. Problem number 1. Write down the Lagrangian equation of motion for a particle of mass m falling freely under the gravity near the surface of Earth. Let us consider a body of mass m falling freely under gravity near the surface of Earth. If x and y axes are taken on the surface of the Earth, then z axis vertically upward, then the kinetic energy and potential energy of a freely falling particle of mass m is given by L is equal to half mx dot square plus half my dot square plus half mz dot square, and potential V is equal to mgz. And we know that L is equal to T minus V. Substituting for T and V, the Lagrangian term becomes L is equal to half mx dot square plus half my dot square plus half mz dot square minus mgz. Then, solving for Lagrangian equation, d by dt of dou L by dou q dot minus dou L by dou q is equal to 0. For q is equal to x, y and z, dou L by dou x will be mx z, dou L by dou y dot will be equal to my dot, and dou L by dou z is equal to mz. However, dou L by dou x and dou L by dou y is equal to 0, and dou L by dou z is found to be mg. Hence, the Lagrangian equations are d by dt of mx dot is equal to 0, and d by dt of my dot is equal to 0, and d by dt of mz dot plus mg is equal to 0. Therefore, mz double dot plus mg is equal to 0 is the required equation for a freely falling particle under the gravity. So the relationship for x and y is found to be mx double dot is equal to 0, my double dot is equal to 0, and for z is mz double dot plus mg is equal to 0. So these are the equations of motion for a particle. If we consider for a particle falling freely under gravity, then we have considered z axis. Therefore, the equation of motion is found to be mz double dot plus mg is equal to 0 is the required equation of motion. Problem number 2. A bead slides on a smooth rod which is rotating about one end with a uniform angular velocity omega. Now I need to set up Lagrangian equation by knowing its kinetic energy and potential energy for a sliding bead. In a plane polar coordinates, The total kinetic energy of the system is given by half m r dot square plus r square theta dot square. And the potential energy with respect to x is given by mg y, that is equal to mg r sin theta. Substituting for t and v in L is equal to t minus v, we obtain L is equal to half m r dot square plus r square theta dot square minus mg r sin theta. So considering q is equal to r, a generalized coordinate, so Lagrangian equation is d by dt of dou L by dou r dot minus dou L by dou r is equal to 0. Differentiating L with respect to r, we obtain mr theta dot square minus mgr sin theta, and differentiating L with respect to r dot, we obtain mr dot. On substituting this dou L by dou r dot and dou L by dou r in Lagrangian equation, we arrive at equation mr double dot minus mr square theta dot square mr theta dot square plus mgr sin theta is equal to 0, which is a required equation of motion for a sliding bead. So students, in this classical mechanics, we have seen how Newtonian mechanics are reformulated by Lagrangian using generalized coordinates, and how Lagrangian mechanics is far superior than the Newtonian mechanics. However, both the formulation are equivalent. Now, let's have a small MCQ session. Question number 1. Total kinetic energy equation for a particle freely falling is given by half m. It is half mx dot square plus y dot square plus z dot square. So option is D. Question number 2. Lagrangian equation for a particle falling freely is, it is half mx dot square plus half my dot square plus half z dot square minus mg z. So option is A. Question number 3. For a freely falling particle, if z is chosen as a coordinate, then the condition is dou L by dou x and dou L by dou y is equal to 0, as well as dou L by dou z is equal to mg. So the option is D. Question number 4. Equation of motion for a freely falling particle is, we see that if you choose z coordinate, we get mz double dot plus mg is equal to 0. So we can choose x as well as y. So the equations will remain same. So the answer is all the above. Question number 5. The constraint of a bead on a uniformly rotating wire in a force-free space is, it is rheonomic constraint. Question number 6. Kinetic energy of a bead sliding on a wire rotating with a uniform angular velocity omega is given by, in plane polar coordinates we have seen, it is half m r dot square plus r square theta dot square. So option is C. Question number 7. The coordinate chosen as a generalized coordinate for a bead sliding on a wire rotating with a uniform angular velocity is, you have chosen R. So option is answer C. Question number 8. Dou L by dou theta is equal to, for a bead sliding rotating with a uniform angular velocity. Here answer it is mr square theta dot. So we solve dou L by, with respect, if we differentiate L with respect to theta dot, we obtain this expression. Question number 10. Potential energy of a sliding bead is, you are saying it is mg r sin theta. Hope you have enjoyed this session. Thank you all.